Okay, let me continue the concept of numerical integration. In the previous lecture, we saw that we can use the Lagrange interpolating polynomial to compute the numerical integration, and I did for n equal to 1. Now, in the second case, let n be equal to 2. When n is equal to 2, it means that x0 should be a, x1 should be a plus h, and x2 is equal to b, where h is the middle point of the a and b. So in fact h is b minus a over 2. Okay, so by the formula we saw that integral from a to b f of x, differential of x, is equal to a0 f0 plus a1 f1 plus a2 f2 plus error of f. Okay, and now here I know that ai is the integral. Here, in fact, ai is integral from a to b, li of x, d of x. So, if I put instead of a0, a1, a2, something like this, I will get, this will be a0 integral from a to b, x minus x1 times x minus x2 over x0 minus x1 times x0 minus x2 d of x plus, and something similar for the second term, but just x minus x0 times x minus x2 over x1 minus x0 times x1 minus x2 d of x plus f2 integral from a to b, x minus x0 times x minus x1 over x2 minus x0 times x2 minus x1 d of x, and I should add the e of f to this formula. Okay, now I have to compute these three integrals for computing the, in fact, the coefficients of the integration formula. Let me compute one. The other two integrals can be computed in a similar way. So let me do one of these. For example, a0, this one, let me call it, of course this one should not be a0, it should be f0. In fact, let me fix it, f0 and so on. Now let me compute a0. a0 is equal to integral from a to b, x minus x1 times x minus x2 over x0 minus x1 times x0 minus x2 d of x. Okay, let's do some in fact change of variable. For example, put x be equal to a plus sh, so d of x is h d of s. So if x be equal to a, so s is 0, right? And when x equal to b, then s is equal to 2. Okay, so this integral a0 should be equal to integral from 0 to 2, okay, and put instead of x a plus sh, a plus sh. Instead of x1, put a plus h, so it should be a minus h, right? And for the second one also a plus sh minus a minus 2h over, and here x0 minus x1 is minus h and minus 2h, so it should be minus plus 2h squared, right? And here I should put ds and also an h appear here, right? So let me do some simplification here to get 0 to 2, a cancel with this a, and here we factor h, we will get s minus 1 times h, okay, and here these two cancel, and if we factor h again we get s minus 2 times h over 2h squared times h ds, right? If you cancel this one, and this one, and move this h out of the integral, we will get h over 2, okay, integral s minus 1 times s minus 2 d of s. And if you compute this integral, this is very easy to computing, just multiply and take integral and put 0 to 2, okay, so it will get, we will get h over 3, okay. And in the same way, exactly, if we do some computation very similar to this, we can find a1 and a2. So similarly, we get a1 equal to 4 over 3 h and a2 equal to h over 3, which we know these coefficients are exactly the coefficients of the Simpson formula. Okay, now let me compute the error term, this one in fact. Okay, now compute error term. For the error term, we have to compute some new things. Note that E of f is equal to 1 over 2 plus 1, it means 3 factorial, a to b, f triple prime at eta of x, x minus x0 times x minus x1 times x minus x2 d of x. We know that this term, if we call it p, pi I equal to 0 to 2 x minus xi, has not a fixed sign in the interval a to b, and the sign changed from x0 to x1 and x1 to x2. So we cannot use the previous theorem. So we have to, in fact, do something else. Okay, so let me write. Since x minus x0 times x minus x1 times x minus x2 has different signs in the interval a and b, so we cannot use the theorem. Okay, so we have to do something else. To compute this error term, write the Taylor expansion of f at x equal to x1 up to 3 terms. Okay, to 3 terms. So f of x should be equal to f of x1 plus x minus x1 times f prime at x1 plus x minus x1 squared over 2 times f double prime at x1 plus x minus x1 cube over 3 factorial times f triple prime at x1, and finally the error term will be x minus x1 to power of 4 over 4 factorial times the fourth derivative of eta x. Okay, now take integral both sides. Okay, we will get integral from a to b f of x d of x, b equal to the integral of this one is a constant, right? So it will be f of x1 at b minus a, and the other one it will be 1/2 f prime at x1 x minus x1 from a, in fact from x0 to x1, right? Yeah, I can write x a to b, or maybe it's better I write from x0 to x1, and for this one it will be plus 1 over, in fact let me write, yes, 1 over 3 times 2, 1 over 6 f double prime at x1 x minus x1 cube, it will be squared, it will be cube from x0 to x2 it's not 1, x2, and finally for this one let me continue, 1 over 4 factorial, it will be 24 f triple prime at x1 x minus x1 to power of 4 from x0 to x2, correct? Yeah, and it's all. And in fact I forget about the last term and I just consider these terms. Okay, so let me continue my computation. For the first one here, b minus a over 2 is h, so b minus a is 2h, so it will be 2h f x1, 2h f at x1. I keep it, okay? And here, if you compute this term, put x2 and x0 and do some computation, finally you will get 1 over 3 h cube f double prime at x1 and 1 over 24 integral from a to b, the fourth derivative at eta x times x minus x1 to power of 4 d of x. Now here in the last integral we know that x minus x1 to power of 4 has a fixed sign in the interval. Okay, now so x minus x1 to power of 4 has fixed sign in the interval a and b, so there exists a number like eta 2 in the interval a of b, such that such that 1 over 24 integral the fourth derivative of eta x, x minus x1 to power of 4 d of x from a to b is equal to the fourth derivative of eta 2 over 24 integral from a to b x minus x1 to power of 4 d of x. And if you compute this integral, it will be the fourth derivative at eta 2 over 120 x minus x1 to power of 5 from x0 to x2. And if you use the fundamental theorem of calculus, you will get this will be f over 60 times h5. Okay, something like this. Except from numerical derivation, f double prime at x1 is 1 over h2 times f x1 minus h minus 2f of x1 plus f of x1 plus h minus h squared over 12 f fourth derivative at eta 1. We have this formula from the numerical derivation or differentiation, in fact. So if you put this f double prime x1, okay, then where? Here. You put it here. Okay, we will get, let me call it 1, and let me call it 2. So put 2 in 1. What we get? We will get integral from a to b, f of x d of x is 2 h f1 plus h3 over 3 times 1 over h squared f x1 minus h will be in fact x0 plus h minus h, so it will be f0, okay, minus 2f of x, it should be x1, in fact, x1, 2f1 plus f x1 plus h, it should be x f2, in fact, yeah, f2 minus h squared over 12, it should be h squared over 12 fourth derivative of f at eta 1 plus h5 over 60 fourth derivative of eta 2. Okay, and if we do some computation here, I will get h over 3. In fact, you multiply, h will be cancelled with this one. In fact, it should be appear here. This h0 3 will cancel which squared, so you will get h over 3 f0 minus 2f, yeah, 2f, and here 2hf. So if you add these two terms, you will get plus 4f1 plus f2 minus h to power of 5 over 12 times 1 over 3 fourth derivative of f at eta 1 minus 1 5 fourth derivative at eta 2. Okay? Now, if you now consider eta be equal to eta and eta 1. In fact, I do not any different. I don't consider any difference between eta 1 and eta 2. So, if we let eta be equal to eta 1 and equal to eta 2, then we get integral from a to b f of x d of x be equal to h over 3 times f0 plus 4 f1 plus f2 minus h5 over 19 fourth derivative of f at eta, and this is exactly the Simpson formula with the error term. Okay, in fact with error term. This is in fact the application of the Lagrange interpolating polynomial to computing the numerical integration.